All right, let's go ahead and get started. We want to continue on with Unit 0. This is the 8th installment. We are going to be continuing with our challenge questions. So let's take a look at number 10. Here's what it says. It says, add the following numbers to the correct number of significant digits. We've got 9.902 grams plus 2.3 grams plus 4.39 grams. Now, the important thing to remember here is that we're looking for the number that is the least precise. The 9.902 is precise to the nearest tenth, hundredth, thousandth. Whatever was used to measure this value is correct to the nearest thousandth of a gram. But look at the second number. The 2.3 is only precise to the nearest tenth of a gram, and the 4.39 to the nearest hundredth of a gram. So I'll let the calculator do the initial work of adding those numbers up. 16.592 is what the calculator tells me, but I have to remember that I can only go to the nearest tenth, right? Because of the fact that the 2.3 is only measured to the nearest tenth. That's how I determine where to round to when I'm adding numbers. So now let's take a look at whether I am going, this is the nearest tenth right here. Do I push that 5 up or not? Well, the number after it is the number 9, which is 5 or bigger. So yes, I do push that 5 up. So 16.592 then becomes 16.6 grams, and that's how I would report my answer. All right? Okay. Let's take a look at number 11. Number 11 says this. Sonia weighs a glass jar and finds the mass to be 3.8 grams. All right? She uses the water displacement method to determine the volume to be 0.434 cubic centimeters. How would she calculate the density to the correct number of significant figures? So the important thing is that we know the formula for density. We know that density is equal to mass per unit volume. Density is equal to mass divided by volume. They're giving me the mass as 3.8 grams, and they're giving me the volume as 0.434 cubic centimeters. So mass per unit volume would be 3.8 divided by 0.434. Easy enough. When I do that on the calculator, here's the number I get, 8.75576. That's what the calculator shows me, but I know I can't have that number of significant digits. I'm dividing, in this process right here, I'm dividing 3.8 by 0.434. The 3.8 has 2 significant digits. The 0.434 has 3 significant digits. The way that I handle division is by taking the lesser of the 2. In this case, it's 2 significant digits. I can only have 2 significant digits in my answer. So I'll round to this point right here, 8.7. The question is, does the 7 go up or not? I look at the next number. If it's 5 or bigger, and it is, then I'll push that 7 up to an 8. It becomes 8.8 grams per cubic centimeter. That is my density to the correct number of significant digits. That's number 11. Let's go on to number 12. Number 12 says, an astrophysicist measures the speed of a comet hurtling toward the Earth at this number of meters per second. Okay? 3, 8, 5, and then there's, let's see, 1, 2, 3, 4, 5, 6. Let me count those again. 1, 2, 3, 4, 5, 6. Yep, that's the number of zeros after the 3, 8, 5, right? So that's certainly moving very fast. It says express this value in scientific notation and explain why this is simply not possible. All right, so to do this, what I'm going to do is I'm going to express it in scientific notation. And that's the exact reason why we use scientific notation. When we have numbers that are very, very big and does have a lot of zeros at the end, or very, very small, have a lot of zeros at the beginning, we're going to use scientific notation to kind of lessen the task of writing that number if we have to do it over and over and over again. So remember that the decimal place would be right here if there were a decimal place. There's not, but if there were one, it would be right there. So we want one number to the left of the decimal, but no more. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8 places to the left to get to 3.85, which would place one number to the left of the decimal, right? And so that means that 385 followed by 6 zeros would be 3.85 times 10 to the 8th meters per second. Now, by the way, that is to the correct number of significant digits because I've got 3 significant digits here. I want 3 significant digits here, right? The 10 to the 8th part doesn't affect significant digits. But there's a problem. And the problem is that there is a constant in the universe called the speed of light. Light travels through the universe at 3 times 10 to the 8th meters per second, and nothing, according to Einstein, can go faster than that. So 3.85 times 10 to the 8th meters per second is simply not possible. Okay? It's simply not possible. The speed of light is the fastest thing in the universe, and so no meteor or asteroid or anything else can go 3.85 times 10 to the 8th meters per second. Okay? So that's that. Number 12. Let's go to number 13. Number 13 says this. It says the density of silver is 9.53 grams per cubic centimeter. If the volume of a sample of silver is 5.3 cubic centimeters, what is its mass? We need to be able to manipulate the basic density formula. We know that the basic formula is density is equal to mass divided by volume. So if I want mass, I'm going to pull volume up, right? I'll pull that up. So I'm going to say density times volume is equal to mass. So what was my density? From the problem, 9.53 grams per cubic centimeter times, the density was 9.53 grams per cubic centimeter. What's my volume? 5.3 cubic centimeters. When I multiply those two numbers together, remember, cubic centimeters on bottom, cubic centimeters on top are going to cancel, and I'm going to be left with grams. Now, the calculator gives me 50.509, but I can't report all those numbers because they're not all significant. I have two numbers, 9.53 and 5.3, and I'm multiplying together, right? This one is 3 significant digits, and this one is only 2 significant digits, right? And so I can only take the lesser of the two. So I'll take the 5 and then one more, the 0. The question is, does the 0 get kicked up or not? If the next number is 5 or bigger, it gets kicked up. It is. Kick that 0 up to a 1, and we get 51 grams as our mass. Remember, that's what we were looking for, and that'll do it for number 13. All right. Next one. Number 14 says this. Determine the volume of this goldfish, all right? So obviously a goldfish is an irregularly shaped object, right? It's not like a cube or even it's not regularly shaped. So if we want to know the volume of that goldfish, here's how we would do it. We would get a graduated cylinder and we would fill it with some volume of water. Now remember that we want to, and I know this is hard for you to see, but we want to measure to the bottom of what we call the meniscus, right? The bottom of this line right here is called the meniscus, okay? So that looks to me to be about 32, right? That looks like about 32. If I look at the other one with the goldfish in it, that to me looks like it's about 38. So the difference between those two is going to be the volume of the goldfish. Looks like the goldfish has a volume of 36 milliliters, okay? 36 milliliters, the difference between 38 and 32. All right, that'll do it for number 14. And let's do one more. Distinguish between a hypothesis and a theory. This one's pretty straightforward. A theory is stronger than a hypothesis. A hypothesis is more like an educated guess. You look around you, you see something about the world that you think to be true, but it's not backed up by experimental data. A theory, on the other hand, is stronger. You make a stronger case because you've done experiments and you've recorded data, and you actually have data to support your idea. We call that a theory. So one more time, the difference between a hypothesis and a theory is that a theory is a stronger argument. It's supported by experimental data. That'll do it for number 15, and that'll do it for Unit 0. I'll see you on the next unit. Thanks. Bye-bye.